All right. So, okay, everyone. Here is the second part of the lecture on backprop, which we began today morning. What we saw today morning was that in order to be able to perform gradient descent to learn the parameters of a neural network, we needed to compute this derivative, which is the derivative of the divergence of between the output of the network in response to a single input and the desired output with respect to the parameters of the network. And in order to do this, we saw that we could use backpropagation, which consisted of two stages. In the first stage, we went forward through the network. They presented the input to the network, and then we stepped through the network using this little algorithm over here, where you set y0, which is the input layer, to be the input. And then subsequently for each layer, you first compute the affine combination of the inputs to the neurons, and then operate on this affine combination using the activation. This was the forward pass. And then so here's the pseudocode for the forward pass. We saw this today morning. And this was followed by a backward pass where you went back through the network and used all of the values that you computed in the forward pass to compute the derivatives of the divergence with respect to the various parameters of the network. So here was the algorithm for the backward pass. We saw this today morning as well. Here's where we stopped. And so in all of this, we've made some assumptions. We made some assumptions about these neurons. We made some assumptions about the activations. And we have to consider some special cases where our assumptions might not be valid. So we've assumed that the computation of the output for any one of the neurons does not directly affect the computation of the outputs for other neurons. We've assumed that the outputs of neurons only operate on affine combinations of their inputs. In other words, they only combine through weighted addition of the inputs. We also assume that the activations of the individual neurons are differentiable. And all of these conditions are frequently not applicable. So these will end up being special cases. The first special case is where we have vector activations. Now, in the case that we assumed that for each neuron, once you computed the affine combination of inputs, there was an activation function that just operated only on that affine combination. So the output of any neuron depended only on the affine combination of the input of that neuron and nothing else. But if you have a vector activation, then the output at any position in response to the affine combination over there not only depends on the zk right there, but also on the remaining zk. So alternately speaking, if I modify this affine combination here, not only will it change this output, it will also change all of these other outputs. So this is what we call a vector activation. I'll call the first case a scalar activation. So in the case of a scalar activation, modifying a single zi only changes the corresponding yi. So I can write yi equals some f of zi. In the case of vector activations, there's a function here which operates on the entire set of affine z's to produce the entire set of y's. So the activation operates on a vector of z's to produce a vector of y's. If I want to plot the influence of the parameters, if I plot the influence diagram, which we introduced today morning, then the influence of any particular z is only on the corresponding y. So this is when you have a scalar activation. When you have vector activations, the influence of any z is on every y. So this z affects not only this y, but also this one and this one and this one. This z affects every one of the y's. This z also affects every one of the y's, and so on. So each zi influences all of the y's. When you have a scalar activation, the derivative rule is very simple. If I want to compute the derivative of the divergence with respect to any z, I just need to compute the derivative of the divergence with respect to the y and multiply that by the derivative of y with respect to the z. So this is just using the chain rule. So the derivative of the divergence with respect to z is the derivative of divergence with respect to y times the derivative of y with respect to z. But then if I have a vector activation, things get a little more complicated. This z influences every one of these y's, and all of these y's in turn affect the divergence. So when I want to compute the derivative of the divergence with respect to this z, I have to consider the influence, all paths of influence between the z and the divergence. So this path, this path, this path, and this path. So to compute the derivative of the divergence with respect to z, I have to sum over all of these y's, and over all the y's, I have to compute I have to add up the derivative over the individual parts of the divergence with respect to z. So this is the sum over all z's of the derivative of the divergence with respect to the corresponding yi's. And this is the sum over all the y's of the derivative of the divergence with respect to that yi times the derivative of y with respect to the z. So this is your derivative rule when you have a vector activation. A special case of this vector activation is the softmax. We've seen this before. So here, the way the softmax is computed, you compute for each z an exponentiation of the z to get the y, but then the y is normalized by the other y's so that the y's sum to 1. So in this case, if I want to compute the derivative of the divergence with respect to z, again, as before, I'm going to have to sum over all the y's, the derivative of the divergence with respect to y, times the derivative of y with respect to z. But then, when I compute the derivative of the y with respect to the z, here's what happens. I have the zi, and this affects yi, but it also affects. So if I have a z1, it affects y1, it affects y2, it affects y3, all of the y's. Now, if I want to compute the derivative of y with respect to z, here's what I have. yi equals e to the zi divided by summation j e raised to zj. That's your softmax. So dyi over dzi is going to be the derivative of e raised to zi with respect to zi times 1 over the summation over j e raised to zj plus the e raised to zi times the derivative with respect to zi of 1 over summation j e raised to zj. So if I expand this out, this first term is simply going to be e raised to zi divided by summation j e raised to zj. This term is going to be plus e raised to zi times the negative of e raised to zi, because this summation also includes the zi terms, divided by summation j e raised to zj whole squared. And this is just yi. And this is simply going to be e raised to zi over summation j e raised to zj times, because this is squared, e raised to zi divided by summation j e raised to zj. This whole thing becomes yi minus yi squared. This is yi, and so is this yi. And so when I compute the derivative of ayi with respect to the corresponding zi, I just get yi minus yi squared. But then if I compute the derivative of some yj with respect to zi, which is one of the diagonal parts, in that case, the equations change a little bit. So here, this is going to be derivative of, or rather, let's say if I'm computing the derivative of yi with respect to some zj, so the derivative of yi with respect to zj, that's a better way to look at it, is going to be e raised to zi, because this is not a function of zj, times d over dzj, 1 over j, 1 over, okay, let me call this k, d over dzk, k e raised to zj, which is going to be e raised to zi times e raised to zj minus of divided by, hey, I should be careful, this is zk, times summation j e raised to zj whole squared, which is simply going to be yk minus, if I'm correct. So I have my indices slightly off on the slides, but you get the idea that I can actually compute the derivative of each of the y's with respect to any zj. And if the derivative is along the line, you get one particular derivative, which is the first term. When the derivative is of a diagonal, you get the second derivative, which is the second term in the row. So overall, what this means is that since this is a vector activation, every one of these terms has a derivative with respect to every one of the z's. Now, I can write, so when I want the derivative of the divergence with respect to z, I have to sum over all the y's and observe that I can actually write both of these derivatives on top using a common notation. I can say the derivative of yj with respect to zi is simply going to be yi times delta ij minus yj. Delta ij is going to be 1 if I equals j and 0 otherwise. And so when I have derivative of yj with respect to zi, if the two are not the same, this guy is going to be 0. You're left with this term. If I equals j, this guy becomes 1, so you're left with this term. The overall derivative of the divergence with respect to any z is going to be summed over all of the y's. The derivative of the divergence with respect to with y times the derivative of y with respect to the corresponding z. If this sounds a little confusing, I recommend that you actually work through the arithmetic. It's fairly straightforward, and this would have been probably been better done in the classroom on a board. But since we are recording this offline, please just go through the slides. Anyway, so this is just one special case of a vector activation. There are other special cases of vector activations. So some of these are mentioned in the slides. I won't go over this during this lecture. Please look them up. So this was one of the special cases. The second special case is with regards to the differentiability of the activation function. We have assumed that the activation functions are differentiable everywhere. And sometimes this is not true. So for example, if you have a rectified linear unit, then for a rectified linear unit, the activation function actually looks like this. And while the activation function is differentiable in all of this region, and over here, right at this corner, it's not differentiable. So in such cases, there are other such activations as well, for example, the max. So, or even the leaky relu, you're going to have hinges of this kind. In such cases, we cannot, when you're computing a derivative at exactly this point, you're not going to be able to find a derivative. Instead, we will use something called a subgradient. A subgradient is of a function at a point is basically the slope of a line or the gradient of a hyperplane, which you can draw such that the entire function, wait, let me do this in two different colors. So if I have a function which is not differentiable at some point, like this one, like the ReLU, then the subgradient is the gradient or the slope of any hyperplane which lies entirely below the curve, touching it at this hinge. So all of these represent subgradients of the function at that point, and traveling along in the direction of the subgradient is guaranteed to increase the function. Now, if the function is actually differentiable at this point, the subgradient is a constant that generalizes, then the subgradient is simply going to be the gradient. Now, Any function which is convex, which sort of curves in this manner, is going to have a subgradient if the function is bowl-shaped. If the function is not bowl-shaped, then you get a more generic concept called quasi-secants, which serve the same purpose. So when you have activation functions like the ReLU, then we actually use the notion of subgradients in order to compute the derivative. So the derivative in all of this region is going to be 1. In all of this region, it's going to be 0. And right at this junction, we have a collection of subgradients to choose from. We typically will use the subgradient, which basically lies exactly parallel to the horizontal axis, and say that the subgradient at this point is 1. Now, there's another special function which also requires subgradients, which is the max. Now, the max activation is also a vector activation, which just picks the maximum of all of the input values. So in this case, the output of this activation is going to be the max of all of the z's. Now, by the definition of the derivative tells you how much perturbing a small value is going to change the output. So if, let's say, the y chose z2, then it means that modifying z1 or any of these other z's a little bit is not going to change y, because the max is z2, and this was the one chosen by y. So in other words, the derivative of y with respect to all of these remaining z's is going to be 0, and the derivative of y with respect to the one z, which had the maximum value, is going to be 1. So this is the derivative for the max function, and this too, it turns out, is just a subgradient. So putting all of these together, the overall approach for training the neural network is here. For each data instance, there is a forward pass where you pass the instance forward through the net and store all the intermediate outputs of all computation. Then there's a backward pass where you sweep backwards through the net and iteratively compute all derivatives with respect to weights. And the actual loss that we try to minimize is the average of the divergence over all of the training instances. This should have been the average. The gradient that we will use in the gradient descent is going to be the derivative of this loss with respect to the parameters, which is the average of the derivative of the divergences for each of the training instances. And once we compute that, then finally we will just use the gradient descent rule in order to update our parameters. So overall, the training procedure is going to look something like this. This is the entire algorithm, the pseudocode for the entire algorithm. You would initialize your loss to 0. You would initialize all your derivatives to 0. You'd initialize all of your parameters. Then for each of your training instances, first you have a forward pass where you pass the instance through the network and compute the output and compute the divergence so that you can just maintain an aggregate of the divergences in order to compute the loss. Then you compute a backward pass where you compute the derivative of the divergence with respect to each of the individual parameters and also aggregate these derivatives so that you get the derivative of the overall loss with respect to the parameter. And then finally, when you've done the forward and backward passes for all of your inputs, you can actually divide the aggregate derivative by the number of training instances to get the average derivative, which is the derivative of the loss. And then the update rule itself is simply going to subtract this derivative times some step size from the current parameters. So this is the entire backprop training. Now, the way we presented it, we spoke of everything in terms of scalars. But in practice, it's much more convenient to think not in terms of what happens to individual parameters, but to think of the entire network in terms of vector operations. Specifically for layered networks, it's much simpler to think of the process in terms of vector operations because the arithmetic is simpler, and also you can use fast matrix libraries to make the operations much faster. And we can restate the entire process in vector terms. This is on the slides, so please read it carefully. In any real system, you will actually implement the vector version of the equations. You will not be implementing the scalar version of the equations. But let's go through the math really quickly again. So here's how you can recast the whole thing in vector terms. So here is one layer of the network. So consider what's happening over here. You have some inputs. You compute some affine combinations of these inputs. These affine combinations are put through activation functions to compute the outputs of the neurons. If I arrange all of these inputs, if there are d of them, if I arrange them as a d-dimensional vector, and then I arrange all of these affine values also as a d1 dimensional vector, where d1 is the number of neurons, and the corresponding outputs y also as, or here, I think this is a dk for the kth layer in general. And then I can similarly also arrange all of the y's in vector format. Now, so the input, the affine combination, and the outputs are all arranged as vectors. These weights I will now arrange as a matrix, where in each row, you're going to have all of the weights going to one neuron. So the first row of the weights matrix is the set of all weights going into the first neuron. The second vector is going to be the set of all weights going to the second neuron, and so on. I can arrange the biases as a vector, where the vector is simply going to be the vector of biases for each of the neurons in the layer. Once I've written everything in this manner, then the computation of a single layer is very trivially expressed in matrix notation. I can just say the affine combination, the zk equals wk times yk minus 1 plus bk. It's basically the matrix product of the weights for the layer with the outputs of the previous layer plus the bias. And yk, which is the output of the kth layer, is simply the activation function applied to the vector of affine values. So you can see that when I write things in this manner, the computation of an entire layer becomes very trivial. And now I can actually write the entire forward pass in terms of these vectors. So I would just set the y0 to be the vector of inputs. Then in the first step, I compute the affine values going into the activations for the first layer as z1 equals w1x plus b1. And then subsequently, the output of the first layer y1 is simply the activation f1 applied to z1, which has been expanded out over here. Subsequently, I can compute z2, which is the affine combination going into the second layer, as w2 times y1 plus b2. And from these, I can compute the output of the second layer, which is y2, which is the activation of the second layer applied to the affine vector, and continue this process all the way to the end till I get the affine combinations that go into the final output layer and then the final activation, which operates on this affine combination to give you the outputs. So the entire computation can be written like so. In the forward pass, I can say the y0, which is the set of values at the input layer, I can initialize them to the inputs. And then for each layer, I compute the affine combination, zk, as wk times yk minus 1 plus bk. And then finally compute the output of the layer, yk, as the activation applied to the affine combination. And the output of the final layer is simply the output of the network. So as you can see, when I write things in this manner, the entire forward computation is very, very simple. So here's the entire forward pass. I initialize the input layer, and then I recurse through the layers, where in each layer, first you compute the affine combination through a simple vector affine formula, and then you apply the activation functions to compute the y's. So once I've done this, I've gone through the entire network from the initial layer all the way to the output. And now I can compute the divergence of the output with respect to the desired output, and then perform the backward computation. But here you must notice that the network is actually a nested function. And this is kind of important. So what happens here? Every layer of the network is actually a function that operates on the outputs of the previous layer. So If you look at what happens in the network, the first layer is a function f1 that operates on an affine combination of the inputs. The second layer is a function f2, which operates on an affine combination of the outputs of the first layer. The third layer is a function that operates on the outputs of the second layer, and so on. So it's basically a nesting of functions till you get to the outermost function, which is the output layer. And now when I compute a divergence of this output with respect to a target, the divergence is computed on y, which is simply the output of the final layer. So the divergence is also a nested function. It's a divergence applied to the output of the final layer, which is a function applied to the output of the penultimate layer, and so on, all the way to the first layer. So this is just a nested function. Now, before I proceed, here's a little bit of calculus. This, we'll just go through a tiny bit of calculus before we continue. Now, in each layer, look at what is happening. There are a couple of different things happening. But first, let's say, consider this layer. Because I'm thinking of everything in terms of vectors, I have this vector of outputs being computed from this vector of inputs. I have the vector of y's being computed from the vector of z's. So the vector of y's is some function of the vector of z's. The derivative of the vector of y's with respect to the z's, y is a vector, z is a vector, so the derivative is going to be a matrix. And this matrix is what we'll call a Jacobian. What you'll observe is this first row is simply the derivative of y1 with respect to z's. Remember, y1 is itself locally, every component of y is a function of a vector. And so the derivative of a scalar with respect to a vector is going to be a row vector comprising the partial derivatives of that scalar with respect to each of the terms of the vector. So this first row is simply the derivative of y1 with respect to these z's. The second row is simply the derivative of y2 with respect to these z's, and so on. The entire thing is a matrix. Now, we can actually write the relationship. You can see that if you write things out in this manner, a small perturbation in y that results from a small perturbation in z is related to the corresponding small perturbation in z through this relationship, delta y equals Jacobian times delta z. You can actually verify this because delta y is a vector of small perturbations of y. I'd write delta y in this manner. So delta y is going to be delta y1, delta y2, and so on. And delta y1 in turn is going to be the partial derivative of y1 with respect to z1 times delta z1 plus the partial derivative of y1 with respect to z2 times delta z2, and so on. And so if you actually work out this equation, when I multiply the Jacobian with respect to delta z, you're going to find that the equation that you get for the perturbations of each of the y's satisfies this relationship that we have here, which we are familiar with, and overall delta y is going to be the Jacobian times delta z. You can work this out. So, having established this, now let's look at what these Jacobians look like for different kinds of activations. When I have scalar activations, each y is a function of the corresponding z, but does not depend on the other z's. So in this case, my Jacobian matrix is going to be a diagonal, where the diagonal entries are the derivatives of y with respect to the corresponding z, and all of the off-diagonal entries are going to be 0. On the other hand, if I have and that derivative, of course, is simply going to be the derivative of the activation. So it's going to be f prime for each of the, that should have been f prime of zi, not yi, for each of the outputs. On the other hand, if I have a proper vector activation, where each output is a function of every input, then the Jacobian matrix is no longer going to be diagonal. Every entry in the Jacobian matrix is going to have some value. And all of the entries are partial derivatives of the individual outputs with respect to individual inputs. Now, so here are some special cases, and these are important. If I have a relationship of this kind, Z equals WY plus B, then the Jacobian of Z with respect to Y is simply going to be this weights matrix W. So also, the Jacobian of, suppose I have this relationship, Y, a vector Y is some function, vector function of some vector function G, or some vector function F of some vector function G of some vector X. Then the Jacobian of Y with respect to X is going to be the Jacobian of Y with respect to G times the Jacobian of G with respect to X. So observe that the order is going to be the Jacobian of the outermost function times the Jacobian of the inner function. Now to see how to see that this holds true, let me write Z equals Gx. So if I write it that way, I can write Y equals F of Z. And from Y equals F of Z, I can write delta Y equals the Jacobian of Y with respect to Z times delta Z. But then Z equals Gx. So delta Z equals the Jacobian of Z with respect to X times delta X. Plugging this value of delta Z out here, the result is going to be delta Y is going to be Jacobian of Y with respect to Z times Jacobian of Z with respect to X times delta X. So this term is what multiplies delta X. So the Jacobian of Y with respect to X is going to be the product of these two Jacobians as written up here. So you can see how the chain rule applies. You have the derivative of the outermost function times the derivative of the next inner function. If I have a nesting of many functions, it's going to be the product left to right of the derivative of the outermost function times the derivative of the next function in, and so on. Now, this is just a minor modification. If the function value that you're computing is a scalar, so if you have d a scalar, which is a function f of a vector g of a vector x, now the derivative of d with respect to x is simply going to be the Jacobian of z of g with respect to, of d with respect to g, d with respect to d, right? No. It's going to be the derivative of d with respect to z times the Jacobian of z with respect to x. Again, you can work it out. If I write z equals gx, d equals fz, then from our relationships, we know that delta z, from our derivative relationships, we know that delta d is going to be the derivative of d with respect to z times delta z. But delta z, again, is going to be the Jacobian of z with respect to x times delta x. Plugging in the delta z value over here, you end up with this relation, which says that delta d is going to be the derivative of d with respect to z times the Jacobian of z with respect to x times delta x. So this term over here ends up being the derivative of d with respect to x. Now here's an important thing to note in all of these. If I have a function which is the derivative of, let's say I have d equals, or some capital D equals f of x, or f of g of x, or any kind of nesting. If the final value in the final variable is a column vector, then the derivative of d with respect to x is going to be a row vector. So here is a scalar function of affine functions. Suppose I have some derivative d, some function d of y, which is written in this manner, that d equals some f of wy plus b. Then the derivative of d with respect to y is simply going to be the derivative of d with respect to z, which is this affine combination, times the derivative of z with respect to y. And the derivative of z with respect to y is simply the weights matrix. And so you can see over here, you can see why this is the case. You can actually plug in all of these formula and this should work out. Now, the derivative of d with respect to b is simply going to be the derivative of d with respect to z. And here is the important one. The derivative of d with respect to w is going to be y times the derivative of d with respect to z. And so here is the second component of this term that I just mentioned. Whenever you have some scalar which is a function of a matrix, so if I have some d which is a function of a matrix, then the derivative of the function with respect to the matrix is going to have a shape. So let's say this matrix is m cross n, then this derivative is going to have shape n cross m. The derivative, the shape of the derivative is going to be transposed with respect to its original shape. So again, if I have the derivative of a scalar with respect to a column vector, the result is going to be a row vector. If I have the derivative of a scalar with respect to a matrix, the shape of the result is going to be the same as the transpose of the matrix. So having gotten all these in place, let's go back and compute our backward pass. So here again is our network. We've used the vector notation so far, so we're going to continue with the vector notation. And I'm going to be using this particular notation. I'm going to say nabla zy to represent the Jacobian of y with respect to z, simply so that I can use a unified notation. I'm going to use nabla ab to represent the derivative of b with respect to a, again, just introducing the notation which is not consistent with what I've used in previous slides, but should help us understand what follows in the coming slides. So here's how I'd go back. The first step I would do is to compute the derivative of the divergence with respect to y. So y, of course, is a row vector, is of course a column vector. So the derivative of the divergence with respect to y is going to be a row vector. Then I take a step back using the chain rule, and now I compute the derivative of the divergence with respect to z. And that is computed using the chain rule. It's going to be the derivative of the divergence with respect to y, which you computed in the first step, times the derivative of y with respect to z, which is the new term. And the derivative of y with respect to z, we know, is simply the Jacobian of y with respect to z. And the Jacobian of y with respect to z, so let's say y is an n-dimensional vector. So this is going to be 1 cross n. And clearly, z is going to be the same shape. So the Jacobian is going to be an n cross n vector, right? And now I can compute the derivative of the divergence with respect to the previous y, which is simply going to be the derivative of the divergence with respect to z times the derivative of y of z with respect to y. And the derivative of z with respect to y, now this is the y of the previous layer, right? So let's say yn minus 1 has, say, some k entries. So the derivative of y with respect to of z with respect to y is simply going to be the weights matrix. And of course we had zn equals w of n times yn minus 1 plus bn, right? So if z was n-dimensional and y was k-dimensional, that means this w was going to be n times k. So this is going to be multiplied by an n cross k matrix. And what would the dimensionality of the result be? It's going to be 1 cross k. And this makes sense because now you are taking the derivative for divergence with respect to a k-dimensional column vector. The result is a k-dimensional row vector. I can also compute the derivative of the divergence with respect to the weights. And so the derivative of the divergence with respect to the weights again. So if I have this row which is size k, and I have this row which is size, say, n, then the derivative of the divergence with respect to this guy is going to be an n-dimensional row vector. Y, of course, is a k-dimensional column vector. This is y, this is z. So the product of, so this is the derivative of divergence with respect to z. This is y. You can see that the product of y and z, of y and the derivative of divergence, the divergence with respect to z, has basically the same, the size of the shape, of the size of this product is the size of the transpose of this weight matrix. So when you compute it, this is going to give you, this simple equation is going to give you the derivative of the divergence with respect to the weights. The derivative of the divergence with respect to the bias is simply going to be the derivative of the divergence with respect to z, which is a row vector of the correct size. Now, having done that, I can take a step back and compute the derivative of the divergence with respect to the previous z, which is simply the derivative of the divergence with respect to y, which has already been computed, times the derivative of y with respect to z. And this term, the second derivative, is simply the Jacobian of these activations. And so I can just write down the Jacobian matrix over here. The Jacobian matrix over here is going to be diagonal because I'm assuming that all of the activations are scalar. Having done this, now I can take a step back, and now I can use the same chain rule and compute the derivative of the divergence with respect to y, and that's going to be the derivative of the divergence with respect to z times the derivative of z with respect to y, which is simply the weights matrix. And so this has already been previously computed. I'm just going to multiply that to the right by the weights matrix. Off the side, I can also compute the derivative of the divergence with respect to the weights matrix, which is y times the derivative of the divergence with respect to z. And I can also compute the derivative of the divergence with respect to the bias, which is simply the derivative of the divergence with respect to z. So having done that, now I can keep going backwards. And now eventually I compute the derivative of the divergence with respect to these affine inputs. And from those, I can compute the derivatives of the derivative of the divergence with respect to the weights and the bias. Now, something to observe over here. In all of that discussion, something very simple might have been missed, so I want you to keep track of this. I began by computing the derivative of the divergence with respect to y. Each time I take a step backward, all that happened was that I right multiplied this derivative by a vector. It was either a Jacobian, as in this case, or when I take a step back, the next term I multiply is a weights matrix. So as I keep stepping back, when I'm computing the derivatives, I compute my initial derivative of the divergence with respect to y. Then I right multiply that by Jacobian, then right multiply by the weight matrix, then right multiply by the Jacobian again, then right multiply by the weight matrix, and so on. Every step backward is just one simple matrix multiplication. And off the side, of course, you also get these derivatives of the divergence with respect to the parameters, which again are very simply computed. The first is an outer product, the second is simply a term that is obtained directly during the back propagation. So here is the overall backward pass. Here's what happens. We're going to initialize the input layer with x, and then you initially compute the derivative of the divergence with respect to the outputs of the network. And then as you go back through the layers, for each layer you would compute the Jacobian for the layer, and then to obtain the derivative of the divergence with respect to z, you just multiply the derivative of the divergence with respect to y by the Jacobian, and then to take a step back and compute the derivative of the divergence with respect to the output of the previous layer, you multiply what you just computed by the weights matrix. And at each step, as off the side, you can compute the derivative of the divergence with respect to the weights, which is the product of the output of the previous layer and the derivative of the divergence with respect to z. and also the derivative of the divergence with respect to the biases, which is simply the derivative of the divergence with respect to z. Now observe again that this looks a whole lot like the forward pass. Here was the forward pass. In the forward pass, you first computed the z as an affine combination of the inputs of the outputs from the previous layer, and then you computed the y as an activation applied to this affine combination. Here, when you're going back, you're computing the derivative of the divergence with respect to y as a linear combination of the derivatives from the next layer, and you're computing the derivative with respect to the affine combinations by employing the Jacobian, which is the equivalent of the activations going forward. So the code would look very, very similar. So here is the overall training algorithm. You'd initialize all of your weights and biases, initialize all the errors to 0, or the losses, and all the derivatives to 0 as well. Then initially you'd go through all of your training instances. For each training instance, you compute the output and the divergence. Then in the forward pass and then in the backward pass, you sort of simply use this very simple update rules to compute the derivatives of the divergence with respect to the weights and the biases, and increment your buffers which store these values so that you're sort of accumulating these derivatives over all of your training instances. When you're done with all of the training instances, you normalize these derivatives by the number of training instances, the t, so that you actually get the average, and then finally update your parameters using your gradient descent rule. And you continue this process until your losses converged. So setting up for digit recognition, say, here's what you do. You'd have a simple problem. For example, recognize something as 2 or not 2. Then your network in this case is going to be a single output with a sigmoid activation. The desired output is either 0 or 1. You typically use the KL divergence. You'd use backpropagation to learn the network parameters. And backpropagation, of course, is going to be computed using this little bit of pseudocode, or code which looks like the pseudocode. If you're performing multi-class classification, you're recognizing the digit. In that case, the data is going to have not just binary labels. Okay, my picture is wrong. I should be more careful over here. I have to fix this picture. But the data for each image is going to have the label of the digit that it represents. And those are going to be computed. You can either have, your network is going to have 10 or maybe 11 outputs, depending on whether you're going to include 0 and 1, 0 and O as separate values. And once you have done that, the output is actually going to be a softmax output layer. The output, in the ideal case, the outputs are going to be, one of the outputs goes to 1, the others go to 0. Using these desired outputs and the callback linear divergence, you'd use backpropagation to compute the derivatives with respect to all the parameters, and then use gradient descent to update your parameters. So this just sort of outlines the entire process. This was possibly the most difficult lecture you're going to have in the course, not because the subject is difficult, but because it's immensely tedious to explain it. And on the other hand, the notion itself is very simple. So you're probably going to have to turn off the audio and just go through the video and the slides to really understand what was being done. But please go through this a few times and really get the idea of backpropagation, particularly the vector variant of backpropagation, because this is going to be important. Now, there are several issues having dealt with all of this. What we've seen is how to compute gradients, derivatives of the loss with respect to all of the parameters of the network, and how to use these derivatives in a gradient descent framework to learn your parameters. But then, will the gradient descent solution actually get to the correct solution? Will it converge? How well will it learn? And how can we improve the ability of the network, of the algorithm, to actually get to the optimal solution? So this is an issue that remains to be discussed. We also want to know will whatever you learn on a given set of training samples generalize to other data which are not part of your training set. Also, what does the output really mean? We've got some values. What do they really mean? We're going to take a look at all of these in future lectures. The next lecture, Wednesday's lecture, is going to deal exclusively with the convergence of the backpropagation algorithm and how well the output is likely to generalize to unseen data. Let's stop right here. Thank you.